6.6 is all about function operations. We're going to learn how to simplify, add, subtract, multiply, and divide different functions together, as well as how to combine two functions in what we call a composite function. First off, we need to know some notation. If we have one function and we're going to represent it by f, and we have another function represented by g, we can do various different operations to put them together. We could add them, subtract them, multiply them, or divide them. The way you're going to be asked to do this could be in two ways, the ones highlighted or their equivalents on the opposite side. Both mean the exact same thing. But since we're combining two functions together, the domain now needs to reflect the fact that the functions are combined. This means that the domain will be a combination of the domain of all the functions that are being put together. Also, whenever it comes to dividing functions, we need to remember that we cannot have a denominator that is equal to 0. So therefore, that will be one of the restrictions to the domain is whatever value would make the denominator become 0. We're going to start off with adding and subtracting. The only difference is that we have to make sure we only combine the like terms. First, we want to know what is f plus g of x. Now remember, this notation just means that we have a function f of x and g of x. It does not mean that we're multiplying by x right now. We're just simply adding those two functions together where x is the variable that we're using. Our function f of x is 4x plus 7, and we're adding to that our function of g of x, which is the square root of x plus x. And with addition, we know that we can actually take those parentheses away, and now it's just a matter of combining our like terms. We only have x's that are the same, so that will now give us 5x plus 7 plus the square root of x as our solution. Now, what if we're doing f minus g of x? We're going to have the same setup, which is 4x plus 7, but now we're subtracting the entire function of g of x. So it's super important to make sure you put it in parentheses. And in the parentheses, we're going to have the square root of x plus x. And that's because we need to remember to distribute that imaginary negative 1 that's on the outside. This now gives us 4x plus 7 minus the square root of x minus x. And we can combine those like terms, which will give us 3x plus 7 minus the square root of x for our answer. Now this brings us to the second part of the problem, of what are their domains. Remember, the domain is a combination of the individual domains of each function. With our first function of f of x, we had 4x plus 7. We want to ask ourselves, are we allowed to plug in any value of x? Are there any restrictions to the numbers we can plug in? Another way to look at it is say, what kind of function is this? This would be the graph of a line, and we know that for a line, we can have both positive and negative x values, which means the domain is all real numbers. But with the function g of x, we have that square root of x. And we know with radicals, we're not allowed to have negatives underneath. That means the smallest value we could plug in for x is 0, so x has to be greater than or equal to 0. Combining those domains, the restriction comes from the x has to be greater than or equal to 0, which tells us the domain for both of these functions will be x is greater than or equal to 0 once they are combined. In the next example, we have two new functions, but we're still going to be adding and subtracting. But this time we want to know what is 2 times f of x plus g of x. That means we need to take the function of f of x, which is 2x squared plus 8, we're multiplying that entire thing by 2. Then we're adding to it the function of g of x, which is x minus 3. We want to make sure we distribute that 2 first, which becomes 4x squared plus 16 plus x minus 3. And we can combine those like terms, which are the constants, leaving us with 4x squared plus x plus 13. Now let's take a look at the domain. For the first function, we have an x squared function, or a quadratic function, which takes on that characteristic U shape. It extends up, but it also continues to extend across the x-axis, and we can square both positive and negative numbers, which means the domain for f of x is all real numbers. With g of x, we have x minus 3, which is the function of a line, which also extends across both the negative and positive x-axis, which also means its domain is all real numbers. Therefore, when we combine those two domains together, the domain remains all real numbers for this function. Now it's your turn. Pause the video and give f minus g of x a try. Make sure that you remember to put g of x in parentheses and distribute that negative, resulting in your final answer. Also, the domain is going to be all real numbers because the domain of the original functions were both all real numbers. The next level is multiplying and dividing the functions. And you've actually been multiplying functions in previous lessons. If we want to do f times g of x, since there's more than one term in both functions, that means we need to use the box method, or you can distribute using your arrows to make sure everything gets multiplied. We're going to have a 3 by 2 box here, which has 3x squared minus 11x minus 4 on top. And on the side, let's do the second function, 3x plus 1. Multiply everything over. That gives us 9x cubed minus 33x squared minus 12x plus 3x squared minus 11x minus 4. We have some like terms to combine across the diagonals here. And this will leave us with 9x cubed minus 30x squared minus 23x minus 4. Now we're ready to take a look at that domain. Our first function, the key here again is that it is a quadratic with that x squared, and quadratic functions have a domain of all real numbers. The second function is linear, since our highest degree of x is just the first power, which also has a domain of all real numbers, which means the domain of our multiplied function is also all real numbers. Next, we'll take a look here at dividing these two functions. We're going to have 3x squared minus 11x minus 4 divided by g of x, which is 3x plus 1. Now, you might be tempted to just stop here, but we always want to see if we can simplify further. And since we have a trinomial up top, we want to try to factor. Using that AC method, so we're going to want to factor just this top part right here, which would give us 3x squared minus 12x plus x minus 4, split down the middle, greatest common factor, which leaves us with x minus 4. And we're going to have 3x plus 1 times x minus 4, and that becomes our new numerator. But we're still dividing it by the denominator, which was 3x plus 1. We can cancel out the common binomial, 3x plus 1, which leaves us with a final answer of x minus 4. Now for the domain, if we look at the original domains, we would say it's all real numbers. But remember that we cannot have the denominator equal to 0. That means we need to take this denominator, 3x plus 1, and we say it cannot be equal to 0, and we'll solve for x to see what value we get. Subtract 1, so we have 3x equals negative 1. Divide, so that means x cannot equal negative 1/3. We can now say that the domain is all real numbers, but x cannot equal negative 1/3. That is the stipulation. Give the next problem a try. Remember, you're multiplying both functions and dividing them. It may be helpful to pull out your factor flowchart when it comes to doing the dividing to make sure you have everything in the simplest terms possible. Here are all of the solutions. Remember, when it comes to dividing, with this x squared minus 9, we could factor it. It is the difference of squares. By factoring, we can cancel out x plus 3, which gives us a final answer of x minus 3. But also, since it was a fraction, we do need to set this denominator equal to 0 to find out the restrictions of the domain, which is x cannot equal negative 3. Now for composite functions. A composite function is a function inside of a function. And it has the following notation. These are two different ways of saying the same thing. Couple of important pieces of information here. First off, this little open circle, it does not mean to multiply. If it was a closed circle, it would, but open circle does not. It means a composite function. And how we would read this is f of x is composed of g of x. Another way of saying that is that g of x goes inside of f of x. That would be the less technical way. And the second way helps us to understand how the order works in these functions. So in our first example, we have two functions, f of x, which is x minus 5, g of x, x squared plus 2. And we want to know what is f composed of g of 3, meaning we need to take this function of g and plug it into this function of f. Whatever's on the inside is always going to get plugged into the function on the outside, kind of working in reverse. There are two different ways that we could solve this problem. The first way is to take f of x, which is x minus 5, and g of x, which is x squared plus 2, and we're going to take the function of g of x, and we're going to plug it into just the x value in f of x. So now we're going to have x squared plus 2 minus 5. But we wanted to know what is f of g of negative 3, meaning we know that instead of x, we're actually replacing it with a negative 3. So now we're going to have negative 3 squared plus 2 minus 5. Well, that's 9 minus 3, which gives 6. Now, the second way to approach this problem would be to look at the notation to start off with, which was f of g of negative 3. And we could start by doing this inside portion. What is g of negative 3? Meaning we're going to take the function of g, which is x squared plus 2, but we're replacing the x with negative 3. Put that negative 3 in parentheses because the entire thing's being squared, and we're going to add 2. And again, that is telling us what g of negative 3 is, which is going to be 9 plus 2, which is 11. Then we can take this part, and we're now going to say, okay, we're taking the answer of g of negative 3 and plugging it into the function of f, which means we're going to do f of 11, which is 11 minus 5, which also gives us that same value of 6. Now in the next example, we're using the same two functions, but notice how the notation has changed. This is g of f of negative 3, meaning that the function of f of x is going to go into the function of g of x. Pause the video and give this one a try using either method 1 or method 2. Here are the worked out solutions. Notice how in both cases we always took the function of f and did that part first. Then we were able to take that function of f and plug it in place of just the x value in the function of g. You replace the x's with a negative 3 because of the notation right here, and your answer will be 66 regardless of which way you solve it. Lastly, the lovely word problem. Let's say that you have a coupon good for $5 off of a large pizza. You also get a 10% discount with your student ID. How much more would you pay for the large pizza if the cashier applies the coupon first? Couple keywords here. How much more? That means we're going to have to subtract the two different options of paying. But before we can do that, the first thing we need to do is we need to find what our functions are. We have one function that we get from the coupon, which we're going to represent by a C. We know the coupon is $5 off of the pizza. Let's say that we represent the cost of the pizza with the variable of P. We're going to take that price and we're going to subtract $5 to figure out how much it costs with the coupon. But we also have the cost with the discount. So we're going to say our second function is D. And it's 10% off, which means you're paying 90%. And we always turn percentages into decimals in math, which becomes 0.9. And you're paying that much of the total price, which we said we're representing by the letter P. Our second step now is to find the composite functions. We need to say, what is the function if we apply the discount first? So we'd have C composed of D. But also we could say, well, what if we applied the coupon and then the discount, which would be D of C of X. And remember, whatever's being applied first is going second because the second part actually goes inside of the first. That means in place of the p in the function for c, we're going to replace it with 0.9p minus 5. In our second composite, we're going to take the function of c and put it into d. So we're going to have 0.9 times p minus 5, which is 0.9p minus 4.5. Then lastly, for step number 3, we are going to subtract. And it asked how much more you'd pay for the pizza if the cashier applies the coupon first. Well, the second composite is where the coupon was applied first, which means we need to use that equation, 0.9p minus 4.5, and we're going to subtract the second option, which was 0.9p minus 5, distribute that negative, so 0.9p minus 4.5 minus 0.9p plus 5. Our p's cancel out, combine those like terms, and we're left with 0.5, which means that they're really saving 50 cents if they apply the coupon before they apply the discount. So these might be some little things that you don't quite think about when you have a coupon and a discount at a store, but the order in which they're applied really does matter.